Good afternoon. I welcome you to the session of experimental methods in fluid mechanics. Today we will continue our discussion on flow measurements. In fact, we have started our discussion on flow measurements, but today we will discuss another module that is thermal anemometry, and we will see that the measurement technique, rather how we can measure flow measurement. If we try to recall what we have discussed, that flow measurement is basically three important flow characters, like it may be volumetric or mass flow rate, or it may be a point velocity measurements, or it is the determination of the flow streamline. In the last lecture we have discussed about the volumetric flow measurement, volumetric flow rate measurement, and for that we have discussed about this flow obstruction flow meter, and also we have discussed about that how we can measure flow rate using drag. But today we will see another flow measurement techniques by which we can measure flow velocity using thermal anemometry. And this thermal anemometry, which is used to measure flow velocity by heat transfer, using in general two important methods, that is either by hot wire or hot field methods. A hot wire, which is approximately 1/10 diameter of human hair, and a hot film is a very thin film or metal film on a glass substrate, and these elements, whether it is hot air or hot film, these elements are electrically heated and placed in a flow from where the heat transfer is measured. And measuring heat transfer, that can be measured by using I square r. Now measuring heat transfer, we can measure what will be the flow velocity. Today we will see that if you would like to measure flow velocity, either using of course using thermal anemometry, maybe hot wire or hot film, we will see their geometric structure, their operational principle, how we can measure, and also we will see the limitations, those we need to consider while using these instruments to measure flow velocity. So today we will discuss about the thermal anemometry. So this thermal anemometry, as I said, this thermal anemometry this is the measurement of flow velocity. This is by using heat transfer. By heat transfer. Now, so thermal anemometer, which are used to measure flow velocity. Now this is the measurement of flow velocity by heat transfer using either hot film or hot wire methods. So how we can measure flow velocity? It depends whether the measurement of flow velocity is directly related to the measurement of heat transfer. When we are talking about measurement of heat transfer, that is either using hot wire, or so I can write using either hot wire or hot film methods. So either hot wire or hot films. Hot wire is basically a hot wire hot wire is a thin wire which is approximately 1/10 diameter of human hair. So thin, and a hot film is thin film metal film on a glass substrate or other metal. So, these elements whether it is hot wire or hot film, these elements are heated, rather electrically heated and placed in a flow field. Then we need to measure the heat transfer, because this hot mass of the thermal mass of the hot air, the thermal mass of the hot air is very small, so that heat transfer adjusts itself instantaneously with a change in flow velocity. So, what we have discussed, this anemometry is one of the reliable instruments which is used to measure flow velocity. Now, the thermal anemometry is used to measure flow velocity using heat transfer, and using heat transfer, now how can we measure heat transfer? We can use either hot wire or hot film methods, and this hot wire is a thin wire which is approximately 1/10 diameter of the human hair, and hot film is a thin film, basically metal film, which is a thin film on a glass substrate or any other material. Now, these elements are electrically heated and placed in a flow field, and as I said that very low mass of this thermal mass of this hot wire, they adjust instantaneously with a change in flow velocity. Now, we will discuss that when we talk about flow velocity, whether can we place these instruments in a flow field which is highly chaotic in nature, or we need to place, even if we place this instrument, rather thermal anemometry, in a flow situation where flow field is highly chaotic, then how we can measure the actual flow velocity using this instrument. And at the beginning I said that when we talk about flow measurements, because in this module we are discussing the flow measurements technique, and this is the sub module where we will be discussing flow measurement, but not the volumetric or mass flow rate, rather it is a point velocity measurement. So, now we will try to draw schematic depiction of the hot wire or hot film thermal anemometry, and from there we will try to see how we can measure heat transfer, and from there we can measure the flow velocity. We will write hot wire. So, if I try to write hot wire, and now these two dimensions are very important, that this is typically of the order of 3 millimeter and this is 1.25 mm, and if I try to draw These are the a few typical dimensions. So, this is the and this is shown in an enlarged view, that is zoomed in view of this part is shown over at the top. The schematic shown in the top panel is the zoomed in view of the portion which is shown by circle in the at the bottom panel. Now, this is typically this is 1.9 mm and distance is 30 millimeter. So, this is a straight, basically this is a straight general purpose hot air probe. So, this is straight general purpose hot air probe, and so this is the straight general purpose hot air probe. Now, a few important dimensions are shown in the schematic, and this is the thin, rather thin wire, and that is 1.25 mm, that is shown the length. Now, the dimensions which are shown over here are the characteristics dimensions. Now, this type of probe, the problem with this probe is, in fact, I didn't mark other things. So, if we look at this is platinum plated tungsten wire, the wire diameter is of the order of 5 micron, overall length is 3 mm, and sensitive wire length, sensitive wire length is 1.25 mm. So, the wire is platinum plated tungsten wire, wire diameter is 5 micron, overall length that is shown in the enlarged view is 3 mm, and but out of this overall length there is a small length which is known as sensitive length, and that length is 1.25 millimeter. Now, there are copper gold plated at the ends to a diameter of approximately micron. So, I can write copper, or I can say copper gold plated, copper and gold plated, copper and gold plated, AU gold plated, at the ends to a diameter of approximately micron. So, at the ends when these wires are connected, copper and gold plated and diameter is of the order of micron. Now, this is basically a straight general purpose hot air probe, and the dimensions which are shown are the characteristics dimension, but this probe is not suitable in places very close to the solid boundary. I mean, if you really would like to measure flow velocity very close in the region or in the zone which is close to the solid boundary, this probe cannot be placed, and this is because of the geometrical structure of the probe. And so, so a probe with offset diameter, rather offset stem, that was developed only to measure, only to use rather this probe in places where would like, rather in fact we would like to measure flow velocity which is very in the zone which is very close to the solid surface. So, that means this general purpose hot air probe is not suitable for those cases where we would like to measure flow velocity in the region very close to the solid surface. To circumvent that problem, an offset stem, I mean probe with a offset stem was developed, and which is geometrically different from this straight general purpose probe. Now we need to see that geometrically that probe, I mean the probe with offset stem, which is also known as boundary layer probe, how the probe looks like. Now we would like to see the schematic depiction of the boundary layer probe. So, probe with offset stem, which is also known as boundary layer probe. That means the general purpose probe as shown schematically in the previous slide is not suitable for measuring flow velocity in the region close to the surface. So, to overcome this problem, this boundary layer probe was developed. So, the objective of having the special type probe is that the general purpose probe that we have seen in the last slide with all its characteristics dimension is not suitable to measure flow velocity in places where which is close to the solid boundary. Now, we will see the schematic depiction of the boundary layer probe. So, if we try to draw, so this is basically a boundary layer probe, the schematic depiction, and this distance is 8 millimeter and this offset distance is again of the order of 3 millimeter, right. So, again this is platinum So, this is sensitive wire, platinum tungsten plated, platinum plated tungsten wire, platinum plated tungsten wire and wire diameter of the order of 5 micron, overall length of the order of 3 mm and sensitive wire length 1.25 mm and copper, gold, and gold plated at the ends, which are, because we need to pass current through this. So, which are at the ends to a diameter approximately micron. So, now from the geometrical structure of this probe, which is known as boundary layer probe, we can see that the offset distance allow this probe to be inserted even in the place which is close to the surface, rather even in the places which is close to, which are close to the surface, and this is used to measure the flow velocity using the same principle. And the characteristic dimensions are almost similar, which we have seen for the general purpose probe, and but the only special rather one important objective that is being fulfilled, rather that was and that was the objective for designing this probe, is that it will be used to measure flow velocity in the region close to the surface. Now, we have discussed that whether it is general purpose probe or it is boundary layer type probe, these two are basically hot wire probe, and now these probes are used to measure heat transfer, essentially to predict the flow velocity. And the as I said that the elements hot wire and hot film, these elements are heated electrically and then placed in a flow field. So, analysis and experimental, I mean when any equipment is designed, then it is required to calibrate that particular instrument before it is used directly for the directly or indirectly for the flow parameters measurement. Now, the analysis and also experimental evidence indicate that the hot wire, so hot wire response. So, I am writing analysis and experiments. Analysis and experiments, which I mean these two evidence indicate that hot wire response is given by I square r, that is A plus B root of u. So, as I said that these elements are electrically heated. So, that is I square into R, because if we pass current through this element I, and if the resistance is R, then it will be I square R. This heat, if we place them in a flow field, that heat transfer will be there by the fluid. So, that is related with the flow velocity by this response, that is I square R is equal to A plus B root u, where A and B, these are the constants and which are determined experimentally, which are determined experimentally, and u is the component of velocity, I can say flow velocity normal to the probe, other normal to the hot wire. So, what we can see that analysis from analysis and experimental, rather I can say I can write experimental, not experiments, experimental evidence, this response, the hot wire response is given by I square R is equal to A plus B root u. A and B, these two are constants which are determined experimentally. Now, u is the component of flow velocity which is normal to the hot wire. Very important to mention here that it is not always the fact that flow will be always normal to the hot wire. So, there might be flow in a velocity component which is parallel to the wire. Now, heat transfer will be affected. So, now we are essentially measuring flow velocity essentially by measuring the heat transfer. Now, if the heat transfer, so if we place in a flow field where it is not expected that the flow velocity will be always normal to the probe, normal to the hot wire. So, the measured heat transfer may not be always equal to the velocity component which is normal to the hot wire. So, the heat transfer because of the velocity component which is parallel to the hot wire will affect the total analysis. So, what I would like to say, the heat transfer that we are measuring, that is not only because of the velocity component which is normal to the hot wire, but the heat transfer will be slightly affected by the flow velocity component which is parallel to the hot wire, but this is very less, and this is not high. So, in fact, that component is very less. So, we are correctly we can say that we actually measure normal velocity component using this measurement technique. So, but I should write at least that point that heat transfer will be slightly affected by the flow velocity component which is component which is parallel to the hot wire, and if this is the case, then measurement, that is we are interested in to measure only the normal velocity component, but and that too by using the heat transfer, but it is not the case always that the velocity components will be always normal to the hot wire. So, the existence of parallel component of velocity rather parallel to the hot wire may slightly affect the measurement techniques, but this is very less. So, we actually measure the normal component, but so this is not we cannot ignore, but at least this is very less, and we can say we actually measure normal component. So, at least I would like to mention another important point in this context here, that if you would like to really measure two components, and it is quite obvious that if you would like to place the probe in any flow velocity field, I mean flow field, their flow field is velocity component, there will have velocity components in three mutually perpendicular direction. So, if you really would like to interested to measure velocity components, rather two velocity components, we can modify the design of the hot wire, and with that modified design we can place the probe in that velocity field, and from there we can measure the velocity component. So, the measurement of the two velocity component, which is not possible using this kind of simple or even boundary layer type probe, but we need to modify the design of the boundary layer type probe or the simple general purpose probe which is used. But again, before I would like to stop my discussion today, I would like to summarize my today's discussion is that, so we have discussed today the flow measurement. In fact, we have started our discussion on flow measurements in the last week. Flow measurements include the measurement of volumetric flow rate, mass flow rate, and also the point velocity measurement, and finally the determination of flow streamline also falls in the category of flow measurements technique. Now, the flow measurement, I mean which is nothing but the measurement of flow, volumetric flow rate and mass flow rate, that we have discussed in last lecture using flow obstruction flow rate measurement, and also by using drag. Today we have discussed about that how we can measure flow velocity, the point velocity, using another important instrument, that is thermal anemometry. Thermal anemometry is used to measure flow velocity by measuring the heat transfer. Normally adopting two methods, either hot wire or hot film. Hot wire, which is used to measure having diameter 1/10 of the human hair, or hot film, which is metal film on a glass substrate or other material. And we have seen that we have schematically depicted the geometrical structure of the probe and the characteristics dimension. We have also discussed the general purpose probe is not suitable for measuring flow velocity in places where flow field is, in places where would like to where the flow velocity would like to measure is close to the solid surface. And if we really interested to measure flow velocity in regions which is close to the solid surface, for that we need to modify the design, and that is probe with offset stem, and which is known as boundary layer probe. And all these probes are basically all these probes are used to measure flow velocity components. Now, I can say of course, if I really interested to measure flow velocity components, then again you need to modify the design, but at least this general purpose probe and the boundary layer probe, these two probes are used to measure normal component of velocity, and the hot wire is electrically heated and placed in a flow field. Now, by measuring the heat transfer, that is nothing but I square R, and this response is given by analysis and experiment using the through this formula, rather by this formula A plus B root u, where A and B are constants which are determined experimentally and use the velocity component. But the velocity component u that we will be measuring using this probe is the normal component, which is normal to the hot wire. It is also the case that even though the component which is parallel to the probe will be very less, but the presence of that velocity component which is parallel to the hot air will affect the heat transfer measurement, which in turn might affect the measurement of the flow velocity component, but as I said that this component is very less. So, we actually measure normal component, rather velocity component which is normal to the hot air. And finally, we have discussed that if we are really interested to measure two component of velocity, which is that one is normal to the air and other is parallel to the air, for that we need to modify the design, and that aspect we will be discussing in the next class. So, with this I stop my discussion today and we will continue our discussion in next class. Thank you.